Hey everybody, and welcome to this video lesson where I'm going to quickly go through, maybe not quickly, but go through each question in the question paper, or at least each topic, and answer the questions for you, and give a little bit of explanation on why they are true or how to approach it. And so let's get started. So first we're going to do paper 1 and question 1. So question 1, variable options are, various possible answers are given and you must choose the correct one. Here we say that we have two forces, F1 and F2, is exerted on, are exerted on a crate standing on a frictionless horizontal surface. The magnitude of F1 is bigger than that of F2, and you can see that. Okay, the crate will, well, what will the crate do? Well, there's a bigger force in the direction of F1 is bigger than F2, so there's a net force acting on this object to the left. Okay, there's no friction, it's frictionless surface, so there's no friction to consider. There's a higher force in the direction of force F1. So what will happen? Net force will cause acceleration. In which direction? Well, in the western direction. So the first answer is B, accelerate west. John stands on a lift and looks at a 20 Newton mass piece fixed to a spring balance hanging from the ceiling. Okay, the reading on the scale is smaller than 20 Newton. Okay, so let me draw this for you, and that's maybe helpful. And so here we have a 20 Newton mass hanging on a scale. Okay, that's 20 newtons. But the reading on the scale is less than 20 newtons. So here is 20 newtons, and this is the actual reading on the scale. So it's less than 20 newtons. So now the question is asking, the correct explanation for the motion of the lift in this short period of time is, well, is the lift moving up, or is it accelerating upwards? Is it accelerating downwards? Or the lift moves at a constant velocity? So if the lift was moving at a constant, is the lift not moving? Well, if the lift was not moving, then it would have read 20 newtons. Okay, so it's definitely not that one. Okay, the lift is accelerating upwards. What will happen if something accelerates upwards? Well, if it's accelerating upwards, it will be experiencing an upward net force. And because it's experiencing an upward net force, there will be not lag, what is it? Also not drag, inertia. Inertia will cause this thing to pull down. Okay, so in other words, there will be a force all of a sudden pulling upwards, so that the force that is applied, the tension here, will not just be the weight, but it will also include the net force acting on the object, on the so in other words, if it is going upwards, then the net force is upwards, and so in that case the tension will be both the weight and the net force, because they're in opposite directions. Okay, so the tension in the, or let me rather write it like this: the net force is equal to the weight, okay, plus the tension. So the tension is, if the tension is the same size as the weight, in other words, this but in the opposite direction, so tension is in this direction. Okay, so now what happens is that the net force, if the tension is, or if the net force, let's write it there like this then, so tension is equal to weight minus the net force. So if the net force is in the opposite direction, then it will increase the reading on here. If the net force is in the same direction, it would decrease the reading. Okay, because the weight will look like it's less. Okay, I'm not going to go into that too much more longer, but the point just being is that the lift is going downwards. For a moment, the weight hanging down on this scale is alleviated as it's accelerating downwards, but then it reaches a constant velocity and it stops doing that. So it's accelerating downwards. That's answer C. A 30 kilogram iron sphere and a 10 kilogram aluminium sphere with the same diameter fall freely from the roof of a tall building. Ignore the effects of friction. When the spheres are 5 meters above the ground, they have the same momentum. Well, momentum is velocity times mass, so no, they won't have the same momentum because both of them have different masses. The same acceleration. Well, what acceleration are they experiencing? They're both just falling off a building, so they're both accelerating at 9.8 meters per second. So this answer is B. Kinetic energy is half mass times velocity squared, so no, it depends on mass. Potential energy is mass times gravity times height. Again, mass is the only difference between these two. Well, obviously they're different, made of different stuff, but that doesn't affect their mechanics really, but their mass does, and it only affects momentum, kinetic energy, or potential energy. The acceleration is only due to the gravitational constant. Okay, 2 trolleys P and Q with mass m and 2m respectively is at rest on a frictionless surface. There is a compressed spring between them. Okay, the spring is released and the 2 trolleys move away from one another. Which one of the following is true? P and Q have equal kinetic energy. Well, again, they've got different masses, so no, they can't have equal kinetic energy. They have different masses. The speed of P is less than the speed of Q, so P has the lower mass, and Q has the larger mass. So the speed of P is less than speed of Q? No, because they will have the same momentum but in opposite direction. In other words, if this one has a smaller mass, it needs a higher velocity. If this one has the higher mass, it needs a smaller velocity, because mass times velocity must be equal for the two. So if this one has a small mass, it has a big velocity. If this one has a big mass, it has a small velocity. So P has the larger velocity or speed. The sum of the final kinetic energies of P and Q is 0. Well, no, because kinetic energy isn't negative, so you can't add 2 kinetic energies and get 0. So no, kinetic energy is half mass times velocity squared. Any square gets rid of any negatives, so no. The sum of the final momentum of P and Q is 0. Yes, this is the law of conservation of momentum. So yes, question D. When an airbag inflates in a car during a collision, the chances of serious injury to the passenger is reduced because is it because the passenger is brought to rest in a shorter time period? Well, no. The shorter the time period is for on which a force is applied or momentum is changed, the higher the momentum. So the point is we have F net is equal to the change in momentum over the change in time. So if we decrease the denominator, the fraction increases. The smaller this thing is that I divide with, the bigger this fraction is. So that will increase the net force experience, so definitely not. The net force acting on the passenger is reduced. Yes, that's true. Is the passenger's change in momentum reduced? No, because his mass didn't change, his velocity didn't change, his change in velocity doesn't change. He goes from, if we put it in, he goes from whatever his future velocity is, initial velocity is. His future velocity is 0 because he's brought to a stop. His initial velocity is whatever that is times mass. So this doesn't change. His initial velocity doesn't change. Okay, what does change is the timing that it takes for him to stop. This timing is increased because an airbag prolongs the time that it takes for it to stop. Okay, so the passenger's change in momentum is increased. Is his momentum reduced or increased? Well, neither. Okay, the net force acting on the passenger is reduced. A net force F acting on a stationary object P with mass 2m over time t produces a change in momentum of y. If the same net force acts on a stationary object Q with mass m over the same time, the change in momentum of Q will be, okay, so we have the same force acting on a net force causing a change of momentum of y. So in other words, we have a net force F is the result of mass 2m produces a change in momentum of y. Okay, let me just think of how to explain this. The same net force acts on a stationary object. Okay, yeah, so let's just reason it out. So the net force is equal to a change in momentum over a change in time. Okay, so a change in momentum is equal to the net force times the change in time. So let's just look at this. So what is the change in momentum dependent on? It's dependent on the net force and on a change in time. Do you see any mass in here? No. So if the net force is constant, F, and the change, the time over which it is applied is constant, so a net force F. Now, the same net force acts on a stationary object Q with mass m over the same time. The change in the momentum of Q will be y. You see, it's the same. It's the same values. If this produces y, it's the same values being applied again. It will simply still produce y. Okay, sorry about that. So question 1.7, a vehicle with mass m is moving horizontally at a constant velocity on a frictionless path. The kinetic energy of the vehicle is k and its momentum is p. The following, the velocity of the vehicle can be given as, okay, so if we just work this out, we have mass m, kinetic energy, so here we go. So P is equal to mass times velocity. K is equal to a half mass times velocity squared. So notice to this, we only want velocity. So what we could do is take this equation 1 and equation 2, and I can say take equation 2 divided by equation 1. And so what do I get? Okay, I get K, my kinetic energy, divided by P is equal to, and then a half mass times velocity squared divided by mass times velocity. So why did I do this? Because I could see that if I divide these two, I'm going to cancel mass and mass. This velocity will cancel with one of those velocities. So taking kinetic energy dividing by its momentum gives me half of the velocity. So if I just multiply both sides with a 2, then I see that taking 2 times kinetic energy divided by momentum gives me my velocity. So those two multiply to 1. So 2k over p, this answer is B. A block with mass m is sliding down a rough surface that makes an angle theta with the horizontal through a distance of x as indicated in the sketch below. The network done on the block will increase if, okay, so the network done on the block, so the work that's done on the block will increase if the greater frictional force acts on the block, the mass of the block is decreased, the distance x is decreased, or the angle is increased. So let's quickly look at the network done on this block. This block is sliding down, so we have the network done. What are all the elements that do work on this block? Well, it can be these. There's applied work, plus or minus work done by gravity, minus work done by friction. Okay, so this is the general formula that it can be. Now, is there work being applied? No, there's no forces acting on it other than it's just sliding down. Is there gravity acting on it? Yes. Is gravity positive or negative? Well, is gravity acting on it? Well, that depends. Is it moving horizontal? If it is moving horizontal, then no. There's no gravity. If it's not, which in this case it isn't, it's going at an angle, then there is gravity working on it. And is gravity an income or an expense? Is it increasing its is it adding to its motion, or is it taking away from its motion? Well, it's sliding down, so gravity is in the favor. So this is positive gravity. Friction is always negative, and in this case it is applied. So let's quickly see here. Work done by gravity is mass times gravity times height. Work done by friction is found by taking the normal force times cos of theta, okay, because it's an object sliding down. The normal force, no, let me just see, mu times the normal force, sorry. It's mu times the normal force. The normal force is mass times gravity times cos of theta, because it is sliding down a slope. And then this is just the frictional force, and then so this is frictional force, and then this must be multiplied by change in x, which in just the distance that it goes. So with all this applied, let's see, we want the network on the block to increase. So here we have all the values now. Will it increase if a greater frictional force acts on the block? So in other words, friction. If this increases, will it increase the network done? No, because it is subtracting. So no, it won't. Okay. If the mass of the block is decreased, where do we have mass? Oh, there we have mass. Okay. If the mass is decreased, you will notice that it won't have any effect, because well, no, it won't have any effect, because it might have an effect on here, but the effect here is greater than the effect there. So no, you can see in both these, so this is mass taken out as a common factor, minus mu mg cos theta times x. If we take it out as a common factor, if mass is decreasing, then this expression will decrease. So no, a decrease in mass will not have a positive effect. Okay, if the distance x is decreased, okay, so the same thing applies. Here, this h is x sine theta. So I can also take out x as a common factor. So if I take out x as a common factor, it will also not decrease the, if I decrease this, that will also not decrease it. Okay. Next is, will it decrease if the angle theta is increased? Now what's going to happen when the angle theta is going to be increased? Well, for one, is the gravity will increase. You see, as it gets bigger and as this angle is increased, the force of gravity is increasing because the normal force is decreasing. So if the normal force is decreasing, gravity is having more of an effect, then the income work is, where's that now? Here. The income work is increasing, the frictional work is decreasing because the normal force is getting smaller. So, and for that reason, this answer is therefore D. A vehicle is traveling at a constant speed towards a stationary observer. Its hooter produces a sound wave of a frequency of 400 Hz. Ignore the effects of the wind. The sound heard by the observer will most likely have a frequency of, okay, so I'm driving towards. If I drive towards, then I'm driving in the direction of my sound waves. So my sound waves are closer together. Let me draw that for you. So this is normal sound waves. Oh, terrible. Okay, let me try this. This is normal sound waves. Okay, so if I'm driving towards the object, then the sound waves look like this. Do you see? As I'm emitting a sound wave, the sound wave looks like this. I'm driving towards the object that's hearing my sound. So what happens to the wavelengths? They are closer together. When wavelengths are closer together, I hear them more frequently. So it's a higher frequency. And so this one's answer is 480. It's emitted at 400, and what I hear is 480. A girl stands next to the road as a fire engine approaches her with its siren blaring and the red flashlights on. She makes the following observation after the fire engine passed her. The frequency of the sound heard, so obviously when something is approaching you, you hear it at a higher pitch. When it passes you, you hear it at a lower pitch. So as it passes, the fire engine passed her. The frequency of the sound heard sounded lower after it passed. Yes, that's true. Sounded higher after, no. Sounded lower after it's passed. So it can only be A and C. Okay, the light. The light appeared visibly the same as after it passed, or it appeared orange after it passed. Now, the only reason why we can observe with our eyes the Doppler effect of distant stars is because they are the theory is that the universe is expanding at such a high speed. You will never be able to see the Doppler effect in light of a vehicle that passes you, because the speed of light, if you look at the formula, it's all about your velocity relative to the velocity of the wave. And the speed of light's velocity is so high that you have to move at such a high speed to have the Doppler effect that it's impossible that we can do that in something as simple as a fire truck. So no change will be visible in the color of the flashlight. Okay, so that is A, and so those are the first 10 questions, first 20 marks. For the first 20 marks, you have 1.2 minutes per mark, so 24 minutes. I have spent 23 and 50 seconds to do this and explain it, and so we are still in time. Thank you for watching. Do you enjoy learning with video? Well, consider doing your matric with Elroi Academy. We've got online courses with video lectures and electronic exercises that you do right on your computer. It's automatically graded so you get immediate feedback. But maybe you like to learn in an entirely different way. Then Elroi Academy is exactly for you. We have an assessment only option where all we provide you is the assessments, and you can study for those assessments in any way you like. A way that's maybe different from the norm, like school. A way that suits you. Whether teacher, tutor, textbook, heck, YouTube for all we care, as long as you pass your assessments. You see, school is not all about passing tests and passing grades. No, it's about learning, and we test your learning using assessments. So we'll take responsibility for the assessments, and you take responsibility for your learning. If you're interested in this, please go over to our website for more information. Anyways, thank you for watching. I hope you enjoyed it, and if you did, please like this video to encourage me to make more. Hope to see you in the next one.